It's time for Security Now. Steve Gibson, the explainer-in-chief, is here to talk about, get ready, get your propeller beanies on. This is one of those special Security Now episodes. He's going to explain a new kind of crypto invented in the late 90s, so it's practically brand new. Fully homomorphic encryption next on Security Now.
Netcasts you love.
From people you trust.
This is TWiT.
Audio bandwidth for Security Now is provided by the new Winamp for Android, featuring wireless sync and one-click iTunes import. Now with free daily music downloads and full-length CD listening parties. Download it for free at winamp.com/Android. Video bandwidth for Security Now is provided by CacheFly at CacheFly.com. This is Security Now with Steve Gibson. Episode 376, recorded October 31st, 2012, Fully Homomorphic Encryption. Security Now is brought to you by GoToAssist from Citrix. Take control of your IT world from one simple cloud-based platform. Provide live or unattended support to all your users, anywhere. Sign up for your 30-day free trial today at GoToAssist.com. Use the promo code SECURITY. It's time for Security Now. Get ready, ladies and gentlemen. Propeller hats at the ready. Here he is, our explainer-in-chief, Steve Gibson. We talk, as always, every week about technology, about protecting yourself, about security, about privacy. But sometimes we get into the weeds. And I don't know, but I'm just looking at the title of today's show, and I think this may be a weedy episode. Hi, Steve Gibson.
Well, you know, Leo, we're not going to have you for 3 weeks. Tom Merritt and I are going to be doing the next 3 Security Now episodes. So I thought we would leave on a high note or a wound-up propeller note or something. We tackled ECC, elliptic curve crypto, 2 weeks ago, of course. And I thought, while we're on the topic of esoteric encryption, we ought to take a look at where the crypto world is today. Everything we've always been talking about is, you know, kind of it's new for us and it's in use now, but it's kind of old and dusty. I mean, you know, all this stuff is like, you know, the RSA patents expired a few years ago, so they're 20 years ago, and you know, even the just chosen SHA-3 secure hash algorithm. That competition began 8 years ago in 2004. So, you know, what's going on right now? And one of the things going on right now, one of the things that cryptographers are actively working on is something called homomorphic encryption or fully homomorphic encryption. And I'll just, before we get into our top of the show stuff, I can explain what it is, that is, and what it accomplishes, and it'll just like bend our brains.
Yeah.
It is possible. It has now been shown. It was hypothesized by the RSA guys back in '78, shortly after they came up with the whole factoring is hard public key encryption technology. They posited the possibility of this, the possibility of homomorphic encryption, but it was an open question. And just 3 years ago, a grad student stunned the world by doing it. And what he did was mathematically demonstrated that it is possible to perform operations like standard computing operations, addition, multiplication, and so forth, on encrypted data without first decrypting it. So you encrypt data.
Wait, say that again.
I know. It's amazing.
What?
So, for example, you could encrypt data, send it to the cloud, have work done on it, never decrypting it. The cloud has no idea what it's doing, Oh, I mean, it knows what what the processing is it's doing, but it never sees any results, no intermediate results. All of everything stays encrypted the whole time. You get your result back encrypted, and only you are able to decrypt the result. And this works. So that's the topic of today's
exciting.
podcast.
I don't understand how it could possibly work, but we'll have to figure it out. And I know we'll find out.
Yes.
I was right. Propeller hats at the ready.
Oh, boy.
Oh boy.
And that might be your costume for today's Halloween podcast.
I should point out neither Steve nor I are wearing Halloween costumes. I wore a trench coat in. But it's because it's going to rain. It's a raincoat. It's not. I should have just said, "Oh yeah, I'm Inspector Gadget." There, Steve's got his TWiT fez on. That's a costume. No propeller on it, however. Nice tassel. Our show. No, you follow the. You're like a kitty cat. You can't. A dog chasing its own tail.
It's a homomorphic tassel.
Our show today brought to you by our friends at Citrix, who are helping IT professionals with an amazing product that just gets better and better and better. You've heard me talk before about gotoassist.com for its remote access. You know, it was a way to remotely, it still is a way to remotely support people. And it has lots of, it's more than just, there's other remote access solutions, but this is one designed for IT. So, for instance, you could do 8 sessions at the same time. You can do unattended sessions. When you work with somebody's computer, you'll get a assay of everything running, all the security software, what exactly, down to the dot, what version of the operating system, all of that stuff. It's also cool because it lets you support Macs or PCs from Macs or PCs or iPads or iPhones or Android devices. So it really has become, because of that, the market leader in support, used by more support professionals than any other remote access solution. But what's interesting is they keep improving it. A lot of companies would just rest on their laurels, as it were, and say, well, we got the best remote support. Why not just stay with that? But no, they've added more. They now have 2 new solutions. GoToAssist Service Desk, which lets you, it's a ticket system, manage, track, and resolve issues. And the thing that I've been getting so excited about, actually, is the remote support. They acquired a company that does, not remote support, remote monitoring. They acquired a company that does monitoring, and they built this into the product. And now you really have everything you need to be a support hero. You've got remote support, service desk, and monitoring. The monitoring lets you proactively track how your clients' networks are working. You'll start by installing the crawler on the network, which automatically detects everything, hardware and software, network attached devices too, so you know exactly what's on there. Every item on the network, and then including software running on all the computers. Then you can set up a dashboard. You can use their built-in modules or customize them to analyze things like server and network performance, CPU, load averages, disk utilization. You can even have a little thing that says how the toner cartridges are doing. This way, before there's a problem, you can go in and fix it. Proactive support. It's the best kind, both for you and your clients. Now, admittedly, your clients will never know. They'll just say, boy, ever since he or she started running our network, we never had problems. Because they will never see the problems, because you can fix them before they become big problems. They don't have to call you. It's good for you too, because you can do this. People like our IT guy, who's a contract guy. He has 350 clients, 3 people. You need something like this to do that. We set him up with GoToAssist, and he loves it. In fact, he's moving over to it because it's less expensive than the much more complicated and much less capable solution he's been using. For remote support, for service desk, for monitoring, to support remotely using mobile devices, to support mobile devices. You got to check it out. Visit gotoassist.com. Find out about how it works, all the security, the SRP, Secure Remote Password Protocol that they use, high-end performance. And then try it free for 30 days. You can try all the features free for 30 days. Just click the Try It Free button and use the promo code SECURITY. I'm telling you, if you're in IT, this is going to take you to the next level. Become a managed service provider or just become a support hero. Go to assist.com, try it free, use the promo code SECURITY. All right, Steve Gibson, we have a little bit, not a lot, but a little bit of technology security news before we get to homomorphic crypto.
I scrounged around looking for interesting things that happened this week.
Quiet week.
And, yeah, the only thing I could find that I thought would be interesting is in our ongoing following of the infamous Do Not Track header that we've talked about for a couple of years now.
Yeah, and as the last I heard, Microsoft is still saying IE10 is going to turn it on by default, which means Apache will ignore it.
Yep. In fact, IE10, I guess, already happened.
Yeah,
and
we have it.
It did not get pulled at the last minute.
Nope.
So not only Apache, but now Yahoo has formally stated that they intend to ignore it. Their term for it is signal abuse.
Oh, wow.
Since the W3C consortium said that it is to be off unless users turn it on, Microsoft, feeling that users would turn it on if they understood what was going on, have it on unless users turn it off. And that's enough for Apache, as you said, and now we know Yahoo to say, okay, we're just going to ignore it.
Apache, I can maybe is a little controversial, but Yahoo's an advertising company, basically, right?
Yes.
So that's not too much of a surprise.
And what's interesting is that Microsoft is planning to make IE10 available for Windows 7, and they intend to still leave it set on unless it's turned off by the user at installation time.
Wow.
So, this will be an evolving story. I'm proud of Microsoft. I don't say that. Have I ever said that? I don't think so.
Wow. What?
They never do anything that I think they should when they should, and they've I'm really impressed. This is great.
You're impressed that they are turning it on.
Yes,
but you're not impressed with Yahoo or Apache for ignoring it.
Not at all. I think they are on the losing side. I think this will be a skirmish for a while. It will end up being decided in favor of the user, which is obey DNT, and IE may get a reputation for being more private because it's got this turned on by default, and maybe other browsers will follow suit. We'll have to see how this happens. It is for me, sort of an interesting little political sidebar on the whole, how our security industry is evolving story. I'm under embargo for some news that I cannot talk about until next week's podcast. I can say only that there will be a significant update to one of our favorite TNO Trust No One cloud storage offerings that I will be able to share with our listeners, and I'm excited about it a week from now. And that's all I could find that was
and there's the news.
And there you have it. Sorry about your commute, listeners.
Well, we're going to get to homomorphic crypto, and if you are driving the car, some of you you will find this stimulating and will wake you up. Others you might want to hold off till you get home. That's all I'm going to say.
Yeah, I actually think this is going to be good. I did want to thank a number of people who said, hey, Steve, this is over the last couple of weeks. What happened to the blinking lights behind you?
Wait a minute.
Because
they're gone?
They are again, but they hadn't been for a couple of weeks.
Oh, I didn't notice.
And I realized, we'd had a brief power outage a few weeks ago, and all three of those little PDP-8s just came to a standstill. And I'm so used to them blinking that when they weren't, I didn't notice it. But people were looking at the video going, hey, the lights have stopped. And so it was when they said, what's going on? I said, oh, that's true. And I started them up again. And I just I wanted to do a shout out about the TV series on Showtime, Homeland.
Oh, I haven't watched it yet. Is it good?
My God.
Now, the premise of this is what?
We're in the second season.
It's like Manchurian Candidate, kind of, right?
We're about we're about 4 weeks in, but last Sunday night's acting with Claire Danes is one of the leads, and some other random guy who we've never seen before, but he's good. it was an interrogation pretty much for most of the hour, but with knowing all the backstory and all of what was going on, and very complex characters that have been painstakingly created. I mean, and she deserves awards, I think, for the job she's doing. Anyway, you can get the discs or find it or borrow it or something for the first season. You need it. You really do need to catch up. But it is just, I don't know where it's going to go, but it has been a season and a third of real fun. I mean, just
no spoilers now. No spoilers.
No, I'm not. I don't do that.
No.
It is really, I think,
because I haven't watched
worthwhile.
any of it. But I should start at the beginning with season 1.
Oh, you have to start at the beginning. Get the first season. You'll absolutely be hooked. And this second season is every bit as interesting. And I have to say, after the first season is ended, it's like, okay, now what are they going to do? And it is certainly the case that a concept can outlive its production. You know, we saw, for examel, Galactica went off the rails like in about season 4 or something, or 3.
It's hard. 4 seasons is hard for any show. Even West Wing kind of went downhill after 4 seasons. It's hard.
Yeah. Then you have the flip side where like Firefly gets canceled before even the ones they've produced have been aired. It's like, okay, yeah.
So I'm looking at Homeland is not on Netflix. Let me see if it is instant video. Amazon Instant Video has it.
Oh, good.
So or you can buy a DVD, but I can stream it on Amazon.
Really, really, really worthwhile.
All right, I'm going to watch it. I'm going to start tonight.
You'll get sucked in. It is. I'll just say, and this is not any spoiler. She works with the CIA. She's a field agent with expertise in the Middle East, and she is also, and this is not a spoiler, she is bipolar, medicated, but secretly, because she could never work for the CIA if they knew.
Oh, that's interesting. How interesting.
Oh, and she's playing her character so well. I mean, it's really good. So, for what it's worth, if anybody has some time to kill or likes,
Damian Lewis always reminds me of Steve McQueen. He has that pursed mouth of Steve McQueen mouth. Yes. And anyway, I tweeted after watching. I was exhausted after the hour Sunday night of this most recent episode, and I needed some coffee. Now, have you opened your bespoke post yet? Your box of awesome. It came, right?
It did. I have it, and I have not opened it. It's sitting in the kitchen waiting for me. I just need to, I have to create the environment for it. So I will do so.
You got the jar of Cafe Integral beans. You've got the AeroPress, which all in sundries. Have you used one of these before?
Oh, yeah.
Okay, so you know about that. Yeah, and, of course, the burr grinder now.
Fabulous.
So this is for power outages. So that you should not be without coffee.
That's true.
If you can build a fire.
My electric grinder does not have a crank on the side.
No, so this is for power outages or those
wait a minute. Oh, I've got UPSs. I can plug it into one of my UPSs. But
you don't need to. It actually does a good job of grinding. Anyway, these guys are a sponsor. I just wanted to mention the Bespoke Post folks. Great geek gift. Don't give geeks. It's a big mistake to give geeks gadgets.
No, we already have what we need.
We know what we want.
And the chargers for them.
Yeah. Don't, you're just asking for trouble. I guess you could give them a gift card, but you want to give them something tangible. And this is a great idea. Plus, it could come every month. It's a subscription club. Members only. If you go to bespokepost.com/twit, you can get, I think it's 20% off your first purchase at Bespoke Post, your first kit. A 1-month gift, $50, 3 months, $135, half a year, $270. It's really nice. I mean, they get to choose free shipping, easy returns. They get to choose if the box is one they want this month or not, kind of like Book of the Month Club. And I got a shaving kit, a variety of stuff, very manly. BespokePost.com/twit to save 20%. And this is the box of coffee. Awesome. We sent you that, Steve, so that you could enjoy. Because we know how you feel. And you probably don't want socks.
I got socks.
The socks sold out. They had these great Argyle socks. They sold out.
Cool.
Yeah. I think you can go back in time. Just visit Bespoke Post and find out. Yep. All right, Steve. I'm ready for homomorphic.
We'll do that in a second because I wanted to share a fun story.
Oh, yeah.
That I was sent by a listener, James V. in Northamptonshire, England, who caught my attention with the subject line, Spinrite produces the evidence. Now, we can probably already guess what that's going to be about, but the details are interesting. He said, "Hi, Steve. Spinrite saves the evidence, or, if you like, Spinrite catches the criminals. We use a lot of standalone video recorders on our customers' sites." This is he's with a security company in the UK. He said, "As you well know, this application treats hard drives very hard, as the 400 H.264 images every second are constantly written to the drives."
Wow.
400?
400 a second.
Maybe he's got multiple cameras. So anyway, he says, "So we get a call from a customer of ours saying that there's been an incident and the police are wanting a copy of the images from our security camera system to permit them to investigate. So an engineer is duly dispatched to the site. No broadband access for security reasons." Of course, he's a Security Now listener, so he understands. You just really can't connect, period. He says, "On arrival, I receive a worrying phone call from the engineer saying that the DVR is, quote, hot enough to fry an egg on and doesn't work properly. Oh, dear. The machine is swapped out and brought back to the workshop where we confirmed that the machine goes no further than the bootloader. We poke, prod, and mess with the drive connections until we get the unit to boot. But guess what? The evidential images we need are on the drive we had to disconnect in order to get it to boot at all. One conversation with our IT guy, and he suggests Spinrite. Now, having listened to the Security Now podcast, I know how Spinrite has saved the day and saved the pizza. But can it save the CCTV? The HDDs are formatted in some form of proprietary Linux configuration by the machine, which locks down the part of the disk used to make it unreadable out of the DVR, both under Linux and Windows. So we were a little unsure, to say the least. The IT guy arrives, plugs the HDD, the hard drive, into a spare desktop and cranks up his copy of Spinrite. The drive makes some strange sounds. But he says in parens, bearings? And then he says, next morning, the drive was a bit warm and Dynastat had done some business. I think it said it had recovered some sectors. So we quit out of Spinrite before it had finished and remounted the drive. Lo and behold, we could access the images, which were quickly exported to DVD. I understand that thanks to the recovered imagery, the criminals were apprehended and had no choice but to plead guilty in court, both receiving custodial sentences. The world is truly a safer place with Spinrite. Without it, there would have been no evidence or conviction. We also have upgraded maintenance contract with a customer, which includes twice yearly HDD checks with, you guessed it, Spinrite. I'll be purchasing a copy of Spinrite on behalf of our customer today, a bargain at around 60 of our GBP. Thank you for Spinrite, and also thank you and Leo and Tom for the great podcasts. Proof now exists that you make the world a lot safer place. James, Northamptonshire, England.
Northamptonshire.
Sure.
Sure.
Are you sure?
I'm sure.
I bet you are.
But you don't say Worcestershire sauce, do you? You say Worcestershire.
You're not going to be sure of anything after we get through with
No, I'm ready to have my brain scrambled.
Okay, when you're talking about homomorphic encryption, you run across sentences like the decisional composite residuosity assumption is the intractability hypothesis upon which this crypto system is based.
Absolutely. I couldn't agree more.
Put that on your T-shirt.
You know, they could write that more clearly. I think that's intentionally turgid.
Well, okay, so RSA Labs glossary definition says of something called probabilistic encryption. This is something we've never talked about before. Everything we've ever discussed has been deterministic encryption, meaning that whether it's a symmetric cipher where we, under the influence of a key, you put something in and you get something different out, and there's a way to reverse that. The idea is every time you put the same thing in, you get the same thing out. But early researchers in encryption a few decades ago were concerned that weakened the system. That is, if you always got out the same thing for what you put in, didn't that coupling create some weakness in the system? So what was and this is a couple decades worth of work, there was this notion of probabilistic encryption where your actual encryption algorithm would produce a different result every time you used it with the same data, so that it broke that deterministic aspect deliberately. And so even if the same data was encrypted, you would get different results. Now, we know, those of us who have been really paying attention will know that we've solved that problem in other means. We have the notion of a cipher like Reindahl, for example, the AES cipher, or any other cipher. But then what we've done is we've created these block chaining modes where we take a so-called initialization vector, an IV, and that is given a pseudo-random value, which can be known. It's okay if we know it. In fact, often it's like it's the start of the message is here's the initialization vector under which we're going to encrypt this block. And then you take that and mix that with your input, then encrypt it. Then you take that encrypted output and mix that with the input of the next block and encrypt it. In other words, you link these together sequentially to create a chain. So that's the way we solve the problem of which truly was a problem of in terms of information leakage, is if you encrypted the same thing and got the same result, then even if someone didn't know what the input was, if they inspected lots of outputs, right, they could see when things were the same and begin to draw conclusions.
So this eliminates that problem. But how is it reversible? That's what I don't get, because you don't know. All right, I'll let you explain.
You're right. It is tricky. Okay, so a whole different approach is probabilistic encryption. So the RSA Labs glossary says probabilistic encryption is a design approach for encryption where a message is encrypted into one of many possible ciphertexts, not just a single ciphertext as in deterministic encryption. This is done in such a way that it is provably as hard to obtain partial information about the message from the ciphertext as it is to solve some hard problem. In previous approaches to encryption, even though it was not always known whether one could obtain such partial information, it was not proved that one could not do so. Now, okay, what that meant is that notice that in all of the crypto we've ever talked about, we've relied on an assumption. That is, for example, it has never been proved that standard RSA public key crypto is safe. It relies on the presumed difficulty of factoring large primes. But no one's ever been able to prove that it's hard to factor large primes. We just know it is. But knowing something and proving it are, worlds apart in terms of academic crypto technology. So what we've done by stepping from the world of deterministic encryption with presumed security is we actually have provable security for the first time. I mean, for the first time, that's one of the things this gives us. So what happened was, back shortly after the original RSA guys invented this factoring-based asymmetric encryption, is they noticed that there was a property that their approach had, this so-called homomorphism. And they wrote a few months after developing RSA about sort of this, they posed this question. Now, homomorphism, look, if we just break the word down, homo and morphic, that means same shape, essentially. And the concept is that you can apply different processes to the same data and get the same result. A simple example would be, for example, the way we know that we can multiply A and B to get a result we'll call C. But we also know we can add the logarithms of A and B in order to get the logarithm of C. And so those are homomorphic operations. That is, A times B equals C, and log A plus log B equals log C. So what happened was this idea just sort of sat doing nothing until just 3 years ago. And one of the cool things about this is now we're talking about state-of-the-art, leading-edge, bleeding-edge crypto, which has got everybody excited. Just 3 years ago, a doctoral candidate, a grad student at Stanford named Craig Gentry, wrote a PhD thesis, and boy, did he get his doctorate. IBM Research snapped him up immediately. So this was in 2009. He stunned the crypto world by laying out a fully working, fully homomorphic crypto system. So what that means is, as I said at the top of the show, is he demonstrated, and I'm going to explain enough of this that very much in the same way as I did 2 weeks ago with elliptic curve crypto, that we'll sort of have a conversational knowledge, sort of a conversational understanding of how this works, I mean, we're not going to go write the code. And for lots of reasons, there are many complexities to doing this. But what Craig demonstrated in his doctoral thesis was that it was absolutely possible to perform addition and multiplication operations on encrypted data where at every stage of the way the data remained encrypted, the result was encrypted, and no one doing that work ever gained any information at all about the nature of the data they were doing the work on. And when the answer then was returned to the person with the key, they were able to decrypt it, and the result after decryption was exactly the same as if that the same operations had been performed on the unencrypted data. So this is huge for the future. This allows, and as I'm reading like people talking or dreaming about applications, I mean, for example, corporations could sub out work on their data in the cloud, leaving it fully secured at all times, and have data processing done on the data with never having to trust. I mean, this takes TNO and squares it, because they never have to trust anyone they hand their data to. They can have it processed and returned. There's actually the cryptologists have designed search engines where your query is never known to the search engine. The search engine doesn't know what results it finds for you, yet it sends them back. And you then are able to decrypt them and get the results of your query with total privacy. And the really interesting applications are in the utterly tamper-proof electronic voting sphere, where it is possible to get anonymity and absolute tamper-proofing in a homomorphic encryption setting. So as a consequence of the fact that this is sort of on the leading edge of what's going on, and that I wouldn't be at all surprised if we start hearing more about this in the future, I thought that now would be a good time to bring everyone, sort of give everyone a sense for how this works. So we need to step back and create some analogies that I will then use to sort of to move us forward. Back in the early days of computing, before digital computers, we had analog computers, and they were patch boards of analog functions. Like you could have an adder, where you'd have like two voltages or two currents, depending upon whether this thing worked on voltage, whether it considered voltage to be the thing that carried the value or the current carried the value, but whichever. It would take two of those and sum them and then produce an output that was that was equal to the sum of the two input values. And you could have a divider where you would put in the two values to be divided, and you would get the result from that. You could integrate. You could basically perform all the standard operations we're familiar with in an analog environment. Now, one of the problems, if you patch together a really sophisticated equation, which is what early analog computer pioneers did, one of the problems is that you would accumulate errors, because as your inputs moved through more of these stages, each stage introduced some error. Could be really, really small, but still it was non-zero. Just due to, for example, temperature in the room could cause some drift in the amplification of the adder, or component, even though they'd worked to trim the component tolerances to be exact, the two inputs to the adder might not have exactly the same signal strength in affecting the output. So, and even simple components like resistors, capacitors, transistors, and back in the day, tubes. There was something in tubes called thermionic noise. But just thermal noise, just actual noise from the physical electron movement in the devices introduced some errors and noise. So the problem was, this was additive as the signal moved through a patch board of these modules, additions and multiplications and integrations and divisions and so forth. And so there was a limit to how much computing you could do before you had a problem with the famous signal-to-noise ratio. That is, the signal being the actual result and the noise being the uncertainty created by the fact that this was all sort of, the best we could do, but not certain. And in fact, it is arguably the fact that digital systems don't have any of this problem, which has allowed digital technology to take off the way it has. As we know, in a digital system, as compared to an analog system. In an analog system, we've got a continuously varying voltage. In a digital system, we decide instead we're going to tolerate some imprecision in the exact specification of a value. That's known as quantization. In return, though, we're going to get absolutely noise-free processing. That noise cannot creep in because at every stage we're dealing with either, as famously, a 1 or a 0, and each stage of our system sort of reasserts the oneness or the zeroness, so that even values that are not quite 1 or 0, when they're being put in, they come out, strongly 1 or 0 on the output. So I wanted to kind of create that picture in everyone's mind of a network of processes that are a little noisy, and the depth of the network that you can create is limited because at some point too much noise accumulates. Because bizarre as it sounds, this bears directly on probabilistic encryption. Imagine a simple cipher, a simple encryption, where you have a single dimension. Think of it maybe like a rope with knots along it, and these nodes or knots represent values that are well understood because of their position, and that the act of encrypting is choosing a node along this line and then deliberately adding some noise. That is, shifting the location a pseudo-random amount away from the proper location. So we deliberately add some noise to the location that we're choosing for a value. Now, the key in this system, the cryptographic key, determines where these nodes are located. And they're not all uniformly positioned. There's a complex calculation for where these nodes are located, so that only somebody with the key knows where the nodes are. Now, we have this notion already of addition, from, like, you take two values and you sum them. So imagine that we create two of these quantities with some noise, and we add them together to get, like on this timeline, on this linear scale, to get their sum. Well, that's going to fall somewhere, and notice that the noise that we added to each of the terms being summed, the noise sums as well, so that our final position will be a function of both of the input terms and both of the noise terms, the pseudo-random sort of fudge factors, the noise that was deliberately put in. Well, as long as that's not too much, as long as there's not too much noise, our sum lands on this scale, and if this is sufficiently large and we have sufficiently large resolution, then that result doesn't mean anything to the person carrying out that operation. That is, all they know is they received a couple values and they added them, but there's no meaning to it because the meaning is a function of where it falls relative to the nodes, sort of the location markers on that scale, and that is only known to the person holding the key. So you sort of see how it's possible to by deliberately adding noise and having an unknown a scale which is not known to the person doing the work, but which is known to the person receiving the answer, that it's possible to sort of subcontract the work of doing the addition, and the person doing it knows they've added a couple numbers, but they don't know anything about the actual underlying data. Well, that's a 10,000-foot sort of sense for how this probabilistic encryption operates. The actual work that is done is not done on a one-dimensional line, or even a two-dimensional plane, or even a three-dimensional space. It's actually done in something in abstract algebra called a lattice, and these are n-dimensional interconnected spaces where the dimensions are like 512 dimensions or 2048 dimensions or larger. So, they're not there's something we can visualize a cube in 3 dimensions, and you can envision, okay, like in 4 space, you'd have families or sets of cubes at the different, in a series of node locations and so forth. So mathematically, you can represent this, even though it's arguably rather difficult to visualize it. And so the way these systems actually work in these lattices is that the work being done is moving a point through this hyperdimensional lattice with noise, so that the processes that are available are addition and multiplication, although it's been shown that we can do anything that we want to with just those 2 operations. So that's from a theoretical math standpoint, that's sufficient. And the problem is that this system that I've described so far is homomorphic in that it satisfies that criteria. But the problem is this noise accumulation, because as you do operations on data that is deliberately noisy, as I said, in the case of addition, you are doubling the noise when you add 2 factors together. In multiplication, you are squaring the noise when you multiply 2 factors together. So noise gets out of hand very quickly, and very much in the same way as with an analog computer, where you can only go so many stages and the noise begins to overwhelm the signal. The way this system works is, once we're done processing, and we're at some location in this hyperdimensional lattice, we need to determine the answer, that is the actual decrypted result, is the node we are closest to. And so you can see that, and so our movement through this n-dimensional space has been deliberately noisy to obscure any actual values, and we need to then determine which final node in this 8,000 dimensional lattice we're physically closest to. So the point is that as we do these processes, the noise accumulates, and that limits how much work we can do. Well, a fully homomorphic system has no limits. That is, by definition, the definition of a fully homomorphic encryption system is one where you can perform any operation that is of arbitrary complexity. And this is Craig's invention. I mean, this amazing insight he had was he said, wait a minute, is it possible to perform a re-encryption of the data in this process? That is, essentially, can this homomorphic encryption perform its own encryption? Because if it can, that is, if there's time to perform this encryption without its own noise overwhelming it, then it's essentially able to re-encrypt the data and zero out the noise. And initially, he was unable to do it, but by using much larger word lengths and a more complex topology, he was able to trade that off for the number of operations needed such that he was able to perform a re-encryption of the data itself without noise getting in the way. And as soon as he was able to do that, he had a fully homomorphic encryption system that can perform any operation that we know of in computation while keeping the data encrypted and never allowing this noise to get out of control, because after some number of steps, then essentially the data is re-encrypted, never returning it to plain text, but sort of re-zeroing out the noise so that it never overwhelms the system. And now, to give some sense for why we're a ways away, his fully homomorphic encryption, he has 4 classes of system sizes. First of all, I should say that IBM Research snatched him up, and he's continuing to work on this. It's been 3 years since his paper was published. After it published, it shocked the crypto world and got everybody excited because they, didn't know what they were going to do for their summer. And they began playing with this. So there have been lots of variations, lots of ideas. I mean, basically, this is an active area of current crypto research. So at IBM, he has built one. He has implemented this, and he was originally thinking that he would use one of the IBM crazy, Watson hypercomputer deals. Turns out they were able to implement this on a much more modest system. He has four sort of scales of the system. He has a toy system, which is, he calls it 2 to the 9th, which is to say it is a 512 dimension lattice. A small one is 2 to the 11th. A medium one is 2 to the 13th, and a large one is 2 to the 15th. And that being, beginning to be practical security. But to give you a sense for why we're a ways away is implementing this system on standard technology computers. And this is why I'm not worried about it in the long term. We're going to fix our computers if we're interested in this to do it. But for example, the somewhat homomorphic encryption system, not the fully, but the somewhat, just in the toy implementation using a 512 dimension lattice requires a bit length for its processing of 200,000 bits. So incredibly long word lengths. The public key used in the fully homomorphic encryption system is 17 megabytes in size. And it takes 2.4 seconds to generate the public key using the fastest available standard machines. The large size fully homomorphic encryption system, that is the one that is 2 to the 15th, which is 32768 dimensional lattice, requires 2 hours to generate the key, which is 2.3 gigabytes in size. So what we have is an entirely different way of encrypting and treating data. And it has almost none of the characteristics we're used to thinking about when we talk about standard deterministic crypto, whether it's symmetric or asymmetric encryption. It's just not suited for the way our current standard computers are structured with 64-bit word lengths. These things need this somewhat homomorphic encryption of the large size, 2 to the 15th, uses a 13 million bit integer to do its work. So we need a completely different technology of computing in order to work with this. The feeling is this has a huge future. We're at the beginning of it, and as cryptography always does, it will get faster, it will get better. People will come up with shortcuts. They'll come up with other ways to do things. There are this notion of noise in a lattice is only one of a number of non-deterministic encryption schemes that have been proposed. There are some others. There are some that use greatest common divisors. There are some that use large families of simultaneous equations where some statistical probability of individual equations being incorrect is a hard problem to solve. And so there are like very different approaches that are being explored. I'm excited because this opens up something like completely new in the field of crypto research, and behind it will be in tomorrow's applications that will work in a way which is completely foreign to the way we're used to thinking of things. And one can imagine, 20, 30 years from now, people will say, well, wasn't crypto always done this way? And it's like, no. What we used to have was really stupid by comparison.
Big improvement.
Yes.
All right. I understood zero of what you said, but I trust that it was all made perfect sense.
Well, the idea is that there is...
What's the executive summary for Leo?
It's that if your data has noise and you know how much noise it has and you want to operate on it, as long as you don't do too much, then the noise doesn't overwhelm the signal, and then you can remove the noise. And that's useful because you can give the noisy data to somebody else, have them do the work, and because it's noisy, they don't get any information from it. Yet the work they do is useful to you because you know how to extract the noise from the signal, the signal from the noise. So there's the even more condensed version.
Good.
And my goal here...
I'm trying to decide whether to pretend I understood that or just go, no.
My goal here, as with elliptic curve crypto, is not to turn us into homomorphic crypto people, but just so that I'll bet you year from now, it'll come around and someone will say, oh, yeah, Google just added homomorphic encryption. Like, oh, well, we know what that is. That's podcast 376 on Halloween of 2012. Go back and listen to it. And you still won't know what it is.
Hey, did you have an opinion? We talked a lot about it during the week, and I think there's probably not much to say, but about the hack of, 3 million plus Social Security numbers in South Carolina.
Yeah, I saw that.
Yeah, I mean, there's nothing much to say. They decided not to encrypt the data.
Yeah, it's unbelievable.
And the rationale was, well, just, it's hard.
Yeah, well, it wasn't encrypted yesterday, and it was just fine.
Yeah. So we didn't need to.
It's still not encrypted today, and we assume it'll be fine. Well, that assumption got broken.
And then, of course, they go on and on about how sophisticated the international hacker. I love the international hacker was, who amazing what the skills this person showed to steal our data. Oh, well, there's nothing much to say.
Someone's secretary clicked on a link. I mean, that's what brought RSA down. Was some administrative assistant clicked a link in email. And that was the entree into the RSA network that allowed them to steal all the private keys.
Yeah, so, I guess the only silver lining is I would hope that CTOs in every other state are looking at South Carolina and going, God, I hope that doesn't happen to us. Maybe we better encrypt our data. But I feel so sorry for the 3 million South Carolinians. Who now some encryption was done apparently on the credit cards. That they used to pay their taxes, but none on the Social Security number and personal information. So they're giving each and every one of them a year's free
credit
report.
Which is, that's nice, but identity theft, boy, I'm sure you've heard the horror stories, Leo, about how difficult it is to get back your identity once it's been stolen.
And the governor of North Carolina said that she and her husband had suffered identity fraud, and it was a very painful thing, and she knows how we feel. So that makes me feel better.
I wonder if they would have a philosophical objection to homomorphic encryption in South Carolina.
I don't know what it is, but it's not God did not intend for probabilistic encryption solutions. It's clearly written that the deterministic solutions are the only approved.
And Leo, if we had done this on April 1st, no one would have believed this podcast. They would have thought, Steve, that is the best darn
what a fake
April Fool's Security Now podcast we have ever heard of.
Oh, lordy.
Right down to the name. They'd go, where did you come up with that?
Come on, you made that up, didn't you?
Oh, God.
Steve Gibson's at grc.com. That's his website. That's where you can get Spinrite, the world's best hard drive maintenance and recovery utility. You can also get lots of free stuff there, all sorts of information, not the least of which is health information. If you go to grc.com/health, you'll find links there to all the books and to our most recent Sugar Hill episode. We did a third episode on Sunday. That's also a TWiT special, I think number 143, but I'm sure you have a link on the website there as well. And 16 kilobit versions of this show. It's for the people who are bandwidth impaired. Transcripts too, which makes it for a show like this kind of important. You can go over it line by line.
You can line your bird cage with it.
No, I think in fact this would be a great exercise for people who want to strengthen their brains.
It'll be an exercise for Elaine, that's for sure.
Elaine's gone. You can follow Steve on Twitter at SGGRC. We do this show I won't be here next Wednesday, but normally every Wednesday, 11 a.m. Pacific, 2 p.m. Eastern Time. That is going to be 1900 UTC next Wednesday because of the we go off summertime.
Yay, we fall back.
Yep, 1900 UTC. However, Tom Merritt will be hosting for the next few weeks as I head down under for a cruise, a geek cruise. So I won't see you till after Thanksgiving. Have a great Thanksgiving.
Will do. Yourself too, my friend. Have a great trip. And
see you in
we'll
December.
Talk to you in 4 weeks.
See you in December, Steve.
Yeah.
See you in... Is that weird or what?
It is.
See you in December. on Security Now.
Security Now.